Hello, welcome everyone to um, Lab 8 for Physics 207 and Lab 9 for Physics 206. This is going to be on Newton's second law, or the laws of motion. Okay, so what I want to do first is I want to give you some theoretical background information on Newton's second law. And basically in this experiment, you want to make sure you watch my video, which shows you how I collected the data. There was a cart on the air track connected. There's a string connected to the cart. It goes over a pulley, and there's a suspended mass hanging from the pulley. And you release that system, and the cart is going to accelerate down the air track, and the suspended mass will accelerate downward. And the whole idea of this lab is to verify Newton's second law. We're going to theoretically calculate what the acceleration of that cart and the suspended mass should be. And then I measured it by using smart timers. And again, you should watch that video to see how I actually did that measurement. And then we're going to compare those two different techniques, calculating it directly and then measuring it. Okay, so let me go to the iPad to give you that background information that you need. Okay, so again, the first thing I want to talk about is Newton's second law. So let's say we have some object, right, and it has a particular mass. So I'll just draw it as a square here. So it has a mass am. And let's say there's two forces acting on this object. Let's say I have a force pulling like this. I'll call this F1. And then say a force pulling up like this. I'll call this F2. Okay, so those are the two forces acting on the object. Now, what we want to do is we want to find the net force, which is the sum of those forces acting on the object. So how do I find the net force? I need to add those two forces together. So you could do that if you had a coordinate system. You could do it analytically, right, by finding the components. Or for now, just to illustrate this, let's just add them graphically. So remember how to add forces graphically, like they're vectors. So I need to add tip to tail. So I would move the tail of F2 to the tip of F1. So it looks something like this. And then I would draw a vector from the tail of F1, tail of the first, to the tip of the last one. So let's say like this. And that would be my net force. Okay, so again, the net force is just the sum of all the forces. So in this case, it just equaled F1 plus F2. All right, so what does Newton's second law say? It says that the net force acting on an object has got to equal the mass times the acceleration of the object. So notice here that the net force is a vector, right? It has a direction and it has a magnitude. So the length of that arrow, F net, is going to be the magnitude. And then it has a direction. You could, figure out an angle with respect to some coordinate system. And on the right-hand side of that equation, MA, M is just a scalar, right? It has a magnitude but no direction. But A has a direction. So it turns out that the direction of the net force is going to be the same as the direction of the acceleration. So this mass is going to accelerate in that direction. Same direction as the net force. Okay. Another thing that comes up is, since this is a vector equation, and it's a very important equation, I'll box it in here. So F net equals MA, Newton's second law. You could also split it up and write it in terms of its components. So I could also write this as F net just in the x direction, right, which is equal to the sum of the forces in the x direction, that's got to equal max. And then I could also write F net in the y direction, which is the sum of the forces in the y direction. That's got to equal m a y. And if you had a third direction, you could also use z as well. Typically in this course, we just deal with two-dimensional motion, right? We rarely deal with three-dimensional motion. So those two equations are equivalent to that one vector equation. So writing things in terms of vectors is a very efficient way of writing equations. Okay, so what I want to do now is I want to derive the acceleration for that system. So remember, if you guys watched the video of me collecting the data, we had a cart, right, that was on the air track. So here's the cart. It had a mass, say m1, and there was a pulley, say right there. There was a string that connected the cart. It went over the pulley, and then we had a suspended mass. So I'll say suspended mass. And that had a particular mass, which we called m2. And when we release that system, so it's on an air track, right? We're assuming friction is negligible for this particular lab. When we release the system, the cart is going to accelerate to the right. I'll just call it A. And because the suspended mass is connected to the cart by a string, right? The string is not stretching or anything. That means the suspended mass is going to accelerate downward with the same acceleration A. So the goal was to figure out A, right? We want to calculate it theoretically. So we want to derive what A should be using Newton's second law. And then in that video, I measured A using the smart timer. So I measured it experimentally. And then we'll compare what we got experimentally from the smart timer to what we actually calculated theoretically using Newton's second law. Okay, so how do we figure out theoretically what the acceleration should be? Well, the first thing we want to do is we want to focus on each object independently. So I'm going to start by looking at just the cart. And I want to create what's called a free body diagram. In other words, I'm going to take that cart, draw it separately, so it's like isolated. And I want to draw all the forces acting on the cart, okay? Well, if you think about it, right, I have three forces acting. I have the weight, which is acting down. So I'll call this W1 is equal to M1G, right? It's the gravitational force. I have what's called a normal force. It's the force that the surface exerts on the object perpendicular to the surface. So in this case, the air track is exerting a force up on the cart. So this is an upward force, which we call the normal force. I'll call it N in this case. And then since the string is attached to the cart, right, I have a tension in the string that's pulling, exerting a force on the cart towards the right. So I'll call that T. And that's it, right? Normally I have a force also going to the left of friction, but because we're using the air track, we can neglect friction. So we'll assume there's no frictional forces, right? Assume friction is 0 in this case. Okay, now what I want to do is I want to create some type of coordinate system so I can apply Newton's second law. Well, in this case, since the object we know is moving to the right, it's accelerating to the right, I'm just going to use my standard coordinate system where I have x going to the right. I'll just dash it in here. So this is like my x-axis. And then y will be going up, positive upward. So this is going to be y here. Okay, so now I'm going to apply Newton's second law in each of those directions. Let me do the y direction first. So for the y direction, I have the sum of the forces, right, in the y direction must equal MAY. That's Newton's second law just for the y direction. So what I want to do is I want basically the y component of each of those forces. And these are really all vectors. I should draw these as vectors. So this is the tension, right, normal, and then the weight is also a vector, and g is a vector. So I just want the y components of each of those vectors. So in other words, I want the y component of the normal force plus the y component of weight 1 plus the y component of the tension, and that's got to equal, this is really m1 in this case, m1 times acceleration in the y direction. Okay, but what is the y component of the normal force? Well, in this case, you don't even need to use trigonometry or anything. What direction is the normal force acting? It's acting up, right? Directly upward. So all of that vector, all of that normal force is in the y direction, and it's positive because it's acting upward. So the y component of n is just n, right? It's all of that n. It's a total magnitude n, whatever that normal force is. What's the y component of the weight? Well, the weight, again, is all acting in the y direction, but it's acting in a negative y direction. So this is going to be negative m1g. And then what's the y component of the tension? Well, if I look at the tension, it's acting, that vector is acting along the x direction. So which part of that vector is in the y? Actually, none of it, right? If you project that into the y, you'd find none of the tension is in the y direction. So this is just 0. And we know that this cart is not leaving the air track in the vertical direction. It's not moving up or down right off the air track. So what is the acceleration in the y direction? It's also 0. So if I solve this for the normal force, I can bring m1g to the other side, or I can add m1g to both sides, and I find that the normal force is equal to the weight, is equal to m1g. So that's true, and normally that would be helpful because if we had friction, it turns out that friction depends on the normal force, and you would need to know that value. In this particular lab, we don't have friction, so yes, that's true, but it's not going to be very helpful. So let's move now to the x direction. So now I'm going to do the same thing. I have the sum of the forces in the x direction. That's got to equal m1ax. Okay, but what are all the forces in the x direction? Well, I want the x component of each of my forces. So I want nx plus w1y, w1x so the x component of the weight plus the x component of the tension, and that's got to equal m1ax. But since the normal force and the weight are acting completely along the y direction, what is their x components? They're both 0, right? So this is like 0 plus 0. And then the tension, since all of it is acting in the x direction and it's acting in the positive x direction, Tx, the x component of T, is just the entire tension T. And that's got to equal m1. And then what is the acceleration in the x direction? Well, it's what we're calling A. Remember, we're trying to figure out what that acceleration is, A. So AX is just A, the thing that we're looking for. So this, I'll box it. It's a really important equation. That's going to be the equation for the x direction. The tension has to equal the mass of the cart times the acceleration. Okay, so let's go now to the other object in our system, which is the suspended mass. And let's do a free body diagram for the suspended mass. All right, so here's my suspended mass. And what forces do I have acting on the suspended mass? Well, I have the weight, right? The weight of the suspended mass. That's acting down. I'll call this W2 now, right? Which is equal to M2G. Again, this is a vector. And then there's only one other force that's applied to the suspended mass, and that's the string again, right? The tension in the string, and that's acting in the upward direction. So acting up. So this is tension. Okay, now in order to apply Newton's second law, we need a coordinate system. I could use the standard x along the horizontal, y along the vertical, right? That standard coordinate system. But the only problem with that is it gets a little confusing because then it flips the acceleration. The acceleration is now negative. So to make things easier, I think this will make things a little easier. I'm going to use this as my coordinate system. Since I know it's going to accelerate downward, I'm going to call that the positive x direction. So if I dash this in here, think of that as my positive x direction. And then the y will just be perpendicular to that. So I've kind of like rotated my coordinate system. Okay, so I have positive x going down and then the y going perpendicular. All right, so now let's apply Newton's second law. Let's do the y direction first. That's the easier one. So I have sum of the forces in the y is equal to m2 now, right? AY. Well, what does it mean to be the sum of the forces? Well, I want the y component of each force. So I want the y component of T plus the y component of the weight. That's got to equal m2ay. Okay, now be careful. Remember, I made y going horizontal, right? And I'm free to choose y however I want. So in this case, y is along the horizontal. So how much of the tension and how much of the weight is in the y direction? Like, what is the y component of those vectors if y is defined to be this, which is going horizontal? Well, none, right? Because it looks like the tension is acting in the negative x and the weight is acting in the positive x direction, and neither of them has any component in the y direction. So these are both zero in this case, based on how I define my coordinate system. These are both zero. And then what is the acceleration of the y? Well, the suspended mass is not moving horizontally to the left or right, so that's also zero. So this equation simply says 0 is equal to 0, which is true, but not very helpful. Okay, so let's move to now the x direction. So let me make sure you can see the picture. So I have sum of the forces in the x equals m2 ax. Well, I want the x component of each force. I want the x component of the tension plus the x component of the weight, right? That's what I mean by the sum of the forces in the x. I have to sum the x components of each force, and that's going to equal m2 ax. But how much of that tension is acting in the x direction? Well, all of it is, right? Because it's directed upward, and actually it's in the negative x direction. So Tx, the x component of the tension, is going to be negative T. How much of the weight is acting in the x direction? All of it, and it's acting in the positive x direction. So this is going to be plus m2g, right? That's the W2, that's the weight. And that's got to equal m2ax. But what's the acceleration in the x direction? Well, it's the same a as before, right? It's the a that we're trying to find. So this is just a. So I'll box this. This is like our second really important equation. Okay, now if you think about it, right? We have that equation. Let me write down the previous equation we found. We also found from before that T equaled m1a, right? So those are our two equations. All right, so the masses I know, right? I basically mass the cart and I mass the suspended mass on the scale. Again, if you watch the video on how I collect the data, you'll see that. So I mass those on the scale. So those are given. The G we know, since we're using CGS units, G is going to be 980 centimeters per second squared. So we know that, it's given. We don't know T, the tension, and we don't know A. And we're trying to figure out what A is. So if you think about this, right, I have two equations, two linear equations, and two unknowns. and I want to solve for those variables. In particular, I want to solve for A. So how do we do that? Well, you guys may have learned a few different techniques in sort of like an algebra class or pre-calc class, where you could use substitution, you could use elimination. Some people will use matrices or determinants. Usually, probably the techniques you know best are substitution or elimination. So in this case, let's use substitution. So where I have a t in my second equation here, so in this equation, this t, I'm going to plug in this expression, right? Because t is the same as m1a. So where I have a t, I'm going to plug in m1a. So I have minus, and then t now is m1a plus m2g equals m2a. And now I can solve that equation for a, right? So I'll add m1a to both sides. Oops. I'll add m1a to both sides. So I'm going to get m2g is equal to, I'll write this as m1a plus m2a. And now I could factor out an a, right, from the right-hand side. So if I take out an a, I'm left with m1 plus m2. And then I could divide both sides by m1 plus m2. And since I want to get a by itself, so it's being multiplied by m1 plus m2, that quantity, I'll divide by that quantity. But whatever I do to one side, I have to do the other side. So these will cancel now. And then finally, I'll write it so a is on the left-hand side. I have a is equal to m2g over m1 plus m2. And that's what we were trying to find, right? That's going to be the theoretical acceleration of the system. So it involves, remember, m2 is the suspended mass. So it's the suspended mass times 980 divided by m1, which is the mass of the cart, plus the suspended mass. That will give the acceleration of the cart and the acceleration of the suspended mass. Usually we say the acceleration of the system. Okay, great. So that when we're asked to calculate the theoretical acceleration, that's the equation that we want to use. Okay, let me switch gears now and go to the handout and explain what you need to do for the lab. Okay, so here is the lab handout. Again, this will be lab 8 for physics 207, lab 9 for physics 206. The first few pages is exactly what I went over. Oh, there's another little subtle detail here. It turns out that we're assuming that the pulley is a very lightweight, low mass pulley, right? It has very low, what's called moment of inertia. And the string is a lightweight string. And that's why we were able to say that the tension here, right, that's pulling on the cart is the same as the tension here, which is pulling on the suspended mass. So that's why I was able to say that these T's are exactly the same, okay? If you had a heavy string or a large heavy pulley, then that wouldn't be the case. But to a really good approximation, that's the case in this lab. So I was able to use that same T in both equations. It's a subtle little fact there. Okay, and then again, our whole goal was to derive that equation. So we derived that equation. So the theoretical acceleration of the system is m2g over m1 plus m2. Okay, so for the first part experiment, again, please watch my video on how I collected the data. It's a short video, it's only a few minutes. It'll just make more sense if you see the actual data being collected for a few trials. I measured the masses. Now, for the first part of the experiment, there were two conditions. There was the mass of the cart by itself, and then we made it a little heavier, the second condition, by adding the two cylindrical weights. And again, you'll see that in the video. And for the suspended mass, that stayed the same for both of these conditions. It was just a hanger, like this little metal hanger, plus a small metal weight. Okay, and these are the masses, and they're in grams. We're going to use CGS units for everything in this particular part of the lab. All right, then for both conditions, I recorded 10 trials, and I recorded the acceleration for those 10 trials, right, using a smart timer. So this is your data. These are the 10 data values for condition 1, right, the mass of the cart by itself. And these are the 10 values for condition 2, the mass of the cart with the 2 cylindrical weights. So question 1, what I want you to do is to calculate the average. So the average acceleration for the first condition, and then the average acceleration for the second condition. Remember, when you calculate the average, right? First of all, you add them up, divide by 10, then make sure you round to the resolution of the instrument, which in this case is 1 decimal place. You want to round it to 1 decimal place. Then you're asked to compute the percent experimental accuracy, right? Remember how to do that? You have to first find all of the absolute deviations. So this second row here is so that you can plug in your absolute deviations. And then you average those, again, rounding to 1 decimal place. And then finally, the percent accuracy is going to be your average absolute deviation divided by your average acceleration times 100. That will be your percent accuracy, right? We've done a bunch of those. Actually, let me, just to remind you, let me do a quick example of how to calculate percent experimental accuracy, because I guess it's been a while since we have done that. So I'm going to go back to the iPad for a minute. Okay. So this is just to remind you how to compute the percent experimental accuracy. So let's say, instead of doing 10, let me do like 5 acceleration values. Let's say these are your 5 acceleration values. And they were in centimeters per second squared. I don't know, let's say we got, 34.2, 33.9, 34.1, 34.0, 34.1. So those are your 3 values. You're going to have 10 values, but I'm just going to do, actually 5 values I meant. So I'm going to do 5 values. You guys have 10 values to do. So first step is to average these 5 values, right? So take out your calculator. Let me do this right now. So 34.2 plus 33.9 plus 34.1 plus 34.0 plus 34.1 divided by 5. I'm getting 34.06, but remember, you have to round it to the resolution of the instrument, which in this case is to 1 decimal place. So I'd have to round this to 34.1. Okay, so that would be my average acceleration. Then the next step, remember, is to create a second column of the absolute deviations. These are also going to be in centimeters per second squared. So that's why I gave you that second row in the table there. You can put all these absolute deviations in. And remember what those are, right? Those are how far each data value, like, so in this case, it'd be how far 34.2 is away from my mean, and how far 33.9 is away from my mean. So you subtract them, but then you take the absolute value, right? So it was basically 34.2 minus 34.1 absolute value. So that's going to be just 0.1. But usually you can do this in your head, right? 33.9 minus 34.1, absolute value is, well, it's a negative 0.2, then absolute value is going to be 0.2. Then 34.1 minus 34.1, that's going to be 0. Then 34.0 minus 34.1 is negative 0.1, but then absolute value is 0.1. And then I guess 0 again. Okay. Then you average these absolute deviations and you round to the resolution of the instrument. So if you add those up, right? And divide by 5. You're going to get, I think it's 0.08. Let me double check it. So 0.1 plus 0.2 plus 0.1 equals divided by 5. Yeah, so I get 0.08, but I'm going to round to the resolution of the instrument, so 0.1. So that's my average absolute deviation. And remember, this always has to be at least the resolution of the instrument, which is 0.1. So in this case, it's exactly equal to the resolution of the instrument. So that's fine. Now to calculate the percent experimental accuracy, so percent experimental accuracy, I take my average absolute deviation, so my 0.1, divided by my average acceleration, and then times, I multiply by 100 to make it a percent. So if I work this out, 0.1 divided by 34.1 times 100, I'm getting around 0.29%, which is good, right? Much less than 1%. So it's very low percent accuracy, which is great. It means there's very low variability in the data. Okay, so you guys need to do the same thing, but for your 10 values for both conditions. Okay, so make sure you fill in this table, right? So now you have your average acceleration, you have your percent accuracy, and make sure you show me the calculations for those percent accuracies, right? You want to show me that final step and how you computed percent accuracy. You always want to show me all your calculations. Okay, question 2. Using equation 3 from above, compute the predicted acceleration, or sometimes they call it the theoretical acceleration. So remember, equation 3 was the one that we derived. So it's this equation right here. A is m2g over m1 plus m2. So that should be the predicted or theoretical acceleration of the system, right, of the cart and the suspended mass. So really all you need to do is plug in your masses, and then g, remember, is 980. And remember, there's 2 conditions. So the first condition, m1, is the mass of the cart by itself. And then the second one, m1, is going to be the mass of the cart with the 2 cylindrical weights, right? But you have all that data because I weighed all the things for you. So you have all that data. All right, then, and by the way, those values from question 2, you want to show me your calculations and fill in the table here. So those would be your 2 predicted acceleration values. The 2 experimental accelerations are just from this previous table. These are your averages, right? So whatever you averaged here for condition 1, without the weights, and then with the 2 cylindrical weights, condition 2, those you can fill in the table here. Those are experimental values. So question 3 is to compare what you got from the equation, your predicted acceleration, to what you got from the smart timer, right? What I measured when I did the lab. So compare them by computing the usual percent experimental error. Remember, you subtract, right, largest minus smallest, and then divide by the predicted times 100, and that'll be your error. So show me both of those calculations for the percent experimental error, right? And then question 2, make sure you show me the 2 calculations for the predicted acceleration. All right, question 4. If you were to maintain the suspended mass, which is what we did in this case, right? So both conditions, the suspended mass was the same. So we maintained the suspended mass, but we increased the mass of the cart by adding the 2 cylindrical weights. What happened to the acceleration of the system compared to when the cart had no weights? Did it stay the same? Did it increase or decrease? So there's a couple ways you could answer this. You could figure it out from your data. You could just look at your data and answer this question. Or you could also look at this equation, the one that we derived, and you could say, okay, if M2 is staying the same and M1 increases, and since this is in the denominator, remember M1 is the mass of the cart. So if increases by adding the 2 cylindrical weights, what's going to happen to acceleration? So either way, you can reason through it using the equation, or you can look at your data, look at your actual values, and you should be able to answer question 4. Okay, experiment part 2. So I made another video, and this is a really short video, on how I collected data for the second part of the experiment. It was basically the same, except now the mass of the cart remained the same. And actually, we left on the 2 cylindrical weights. So M1 is now the mass of the cart with the 2 cylindrical weights, right? That just stayed for all 4 conditions. It's going to be 4 conditions now. And what changed was the suspended mass, right? It increased, basically. We varied it. So in the first case, the first condition, the suspended mass was the hanger plus a small metal weight. Then the second condition was the hanger plus a small metal and a large plastic mass. Then the third was the hanger plus large metal and large plastic. And then the fourth was hanger plus small metal plus large metal and large plastic. So all 4 together. So basically what we're doing is we're slowly increasing the mass over these 4 conditions. So I masked everything for you on the scale, and that's in this first column here, right? These are your 4 conditions. So this is the hanger plus a small metal weight, right? That's the same as before. Small metal plus large plastic, small metal and large metal, and then all 3 of them, small metal, large metal, and large plastic. So those are the masses in grams. We performed 10 acceleration trials again for each of those masses. Remember, the cart was always the same. It was a cart with the 2 cylindrical weights. And these are the values that I got for the acceleration for the 5 trials. Okay, so what I want you to do for question 6 is, first of all, find the average acceleration for each of these conditions. Right? So the average, the 4 averages here. And then on the last column here is the tension in the string. And it comes from that second formula that or second equation that we derived using the suspended mass. So we just, if you rearrange that equation, you can put it in this form. So it involves the suspended mass. So how do you calculate T here? You're going to use M2, which is given here, right? Depends on your condition. So let's say in the first case, it'll be 6.9. G, of course, is 980. And A is going to be your average acceleration, 22 point whatever it is, whatever that average is. And that'll give you the tension. Now, be careful. It's going to seem weird, the values you might get. You're probably going to get values like maybe 6,000 plus, and then it goes up even higher to, I think the last one was somewhere around 17,000. That is correct. The values are large only because of the units that we're in. We're not used to using these units. The units for force in CGS are what's called dynes. Okay, so if you're getting values that are large, like 6,000, that is correct. You're doing it correctly. All right, so show me those calculations for the tension. And then I want you to do a plot. So go to Pascal Capstone, plot this column, the average acceleration on your X, and plot tension on your Y. So average acceleration will be on the X-axis, tension will be on the Y-axis, and make sure you also include 0, 0. It's not in the table here, but the first point should be 0, 0, right? If there's 0 acceleration, there's 0 tension. And then it'll be this value on the X and that tension on the Y and so on. So X values, Y values. You want to do a linear fit, right? So you're going to plot it, then do a linear fit. Don't forget to give a title at the bottom, right? Tension versus acceleration. And then when you do the linear fit, remember, it'll give you the slope value. Well, what does that slope represent? Well, we know from the other equation that we derived that tension is equal to the mass of the cart times acceleration. And since I'm plotting tension on the y-axis and average acceleration on the x-axis, this is just a linear equation, right? It's like y equals mx plus b, where b is 0 in this case. So what is the slope? The slope is going to be the mass of the cart. In fact, in this part of the experiment, it was the mass of the cart with the 2 cylindrical weights because we left those 2 cylindrical weights on. So when you record the slope here, in theory, it should equal the mass of the cart with the 2 cylindrical weights. Okay? So the last thing I want you to do is, well, there was another way we can get the mass of the cart with the 2 cylindrical weights. We could just weigh it on the scale, right? And I did it up above. So that was right here. So this mass of the cart with 2 cylindrical weights, 289.7 grams. So I rewrote that back down in this table. So I'm calling this the measured mass of the cart with the two cylindrical weights. Think of it as like your experimental mass. The predicted mass comes from the slope of your graph. Don't forget to include the graph in your lab report, right? So copy and paste it into your lab report because I want to see that graph. And then you just want to compare these two values by computing a percent experimental error. And it should come pretty close. Like you might get like around 300 for your slope, and that's actually very close to 289.7. Okay, so compare them by computing the percent experimental error. Which one should you divide by? Divide by this one, by the predicted one. All right, and then the last part of this experiment, we're going to play around with another simulation. Okay, we're not going to do too much with this, but thought it might be fun to kind of play with forces and accelerations and net force with the simulation. So there's a simulation called forces in motion. You want to use this link. I will also post this separately on Brightspace, so you have that link. And here's what you want to do. Let me actually go to that site and explain what you need to do. I have it written here as well, but it'll be easier if I just show you. Okay, so here is the simulation site, and you want to choose the one Forces in Motion Basics. We're going to click on it. Right, it should load up. And then I want to choose acceleration. Okay, so here's my object, right? It's a wooden crate. And I want to make it a little heavier, so I'm going to put this child on top of the object, right? So now I have like the total mass of the crate plus the child. And then this guy is the guy who's going to be applying a force to the crate and the child, to that system of the crate and the child. And there's also friction, right? So there's going to be a force that resists motion that's going in the opposite direction. It'll be going to the left. The applied force, I'm going to have it going to the right, so he's going to be pushing to the right. There's going to be a resisting force, what's called a kinetic frictional force. We'll talk more about kinetic friction in the next lab. But for this lab, you just have to know that it's going to resist the motion, right, once you start moving. And what I want you guys to do is to check off forces. That one should already be checked. Check off the sum of the forces, values, masses, and speed. But do not check off acceleration. I want you to calculate the acceleration, and then we will check it off later to figure out if we were correct or not, okay? Now, I want you guys to use 300 newtons, but just so I don't have exactly the same value, I'm going to do something different. Let's say, I do 400, just for an example, 400 newtons. Okay. So what that means is that the person is exerting applied force of 400 newtons to the right. There's going to be a frictional force. Once it gets moving, there's a kinetic frictional force of 225 newtons to the left. Actually, let me see if it stays that value. No, I guess it drops. Okay. So there's a kinetic frictional force. That was a static frictional force. There's a kinetic frictional force of 169 newtons to the left. That means, let me pause this for a second. That means the net force, if I add the force going to the right minus this force going to the left, I've got a net force going to the right of 231 newtons. Remember, Newton's second law, right? F net equals ma depends on the net force. It's the net force that equals the mass times acceleration. So when you apply Newton's second law, you want to use the net force here, whatever this net force is. Remember, you're going to make it 300 newtons, but I'm just using 400 as an example for the applied force. Okay, once you have that, right, once you know the net force and you know the total mass, so in this case, the total mass will be 90 kilograms, you can calculate, you can compute the acceleration of the system, right, as the person is speeding up, right? And you'll see the speed, it's going to reach 40, and then the person's going to stop pushing. So let me show you that. So you want to calculate the acceleration at some constant value right now. And then once it reaches 40, see how the person stops pushing? And now look what's happening. There's no longer an applied force, but there still is a kinetic frictional force going to the left of 169 newtons. That means that the net force, the sum of the forces, since it's the only one acting, it's also 169 newtons pointing to the left. Now you want to calculate the acceleration again as the box, the crate, and the child are slowing down. Okay, so we have this force going to the left, so that's like negative 169, and that's got to equal the mass 90 times the acceleration. So you can compute the acceleration. It's going to be a negative value in this case, right? So compute the acceleration when the person was speeding up, and then when they were slowing down. All right, then you're going to do the whole thing again, but now you're also going to click on acceleration. Actually, let me stop this. You're going to use 300, but I'm going to use 400 again, just as an example. Okay, so I'll start it. And as the speed is increasing, right, there's a net force. It's constant net force, so there's going to be a constant acceleration. So in this case, the acceleration was like 2.57 meters per second squared. And then you want to see how close your calculation came to that, that value that we got from the simulation. So you're comparing those two values. Just qualitatively comparing. You don't have to do a percent error or anything for this part. And then once, I'll keep playing it, once it reaches 40 meters per second, the person will stop pushing, right? They let go. And now the only force acting is the frictional force. And if you calculate the acceleration, you're going to get some value, in this case, a negative 1.88 meters per second squared. And you want to compare your value to this value right here. And actually, eventually, because friction is slowing it down, slowing it down, slowing it down, eventually it's going to stop. And now there's no forces applied anymore, and the person's at, and the child and the crate are at rest. Okay, so do that where you calculate the acceleration first, and then you actually click on it to measure it from the simulation, so you can compare what you got from the calculation to what you measured from the simulation. Then I want you to do the whole thing again, but now instead of putting the child on, put on another crate. Right? Again, click all these first, accept acceleration, apply the force of 300 newtons. Again, I'll do 400 just as an example. And now you know that the net force, right? This is the applied force, this is the frictional force, so this is the net force. The net force has to equal ma, so you can calculate acceleration. Then later you can check it to see how close you were. And then same thing, once the person stops pushing, right? Once they reach 40 meters per second, they stop pushing. Now there's just a frictional force, so calculate that acceleration, it'll be negative, and then you can check it to double check what you got. Great, so let me go back to the handout and we can finish. Okay, so again, I kind of explained everything anyways, going through the simulation, but all the information is in here as well in the handout. And all I want you to do for this last question is fill in this table. Show me your calculations that you got for the acceleration when the person was pushing the crate, right, and the crate was speeding up, right, and the object consists of the crate and the child on top of it. And then when the person stopped pushing, right, and it was decelerating, calculate that acceleration. Remember, this one should be negative. And then write in the values that you got when you clicked on that acceleration check mark when you got or measured the acceleration from the simulation itself. You're going to put in those values. And they should be really close, right? If not exactly equal. Then do the same thing, but instead of having the crate with a child on top, just do two crates, put one crate on top of the other. And then same thing, calculate acceleration when the crate is accelerating to the right, when it's speeding up, and then when the crate is slowing down, the acceleration is to the left, right? And then compare that to the measured. And again, you just have to qualitatively compare them. You say, oh yeah, we got exactly the same thing as the measured or whatever, but show me these 4 calculated accelerations for your lab report. Great, that's it. So that's it for this lab. And then the next video will be on lab I guess it'll be lab 9 for physics 207 and lab 10 for physics 206. And that will be on friction. We'll talk more about friction. Great, thanks.